Recording started.
Hello, Dean Atkinson again, presenting on what would probably be the third week of lab in Expt227, the General Chemistry Lab at PSU. This weblet is titled "How Much Sugar is in a Can of Coke?" as is the experiment you're going to be doing in lab this week. So as the name implies, we'll be determining the number of grams, or the mass of sugar that's in a can of Coke. You probably have heard repeatedly from dentists and from your mom that it's not a good idea to drink a lot of sugary sodas, and we'll find out exactly how much sugar is in one of those sugary sodas that you might be drinking. And I think it'll be fairly surprising to most people how much is in there. The why, pretty much we're interested in finding out amounts of stuff. So there's a whole branch of chemistry that's called analytical chemistry that is specifically devoted to finding out what is in substances and how much specifically. So quantitative analysis, quantitative meaning how much, also qualitative analysis, what type of stuff is in different substances, and it branches out into all of the cool forensic chemistry that's so popular right now. So lots of interest in this type of measurement. In this case, we will be using a couple of different physical properties to measure the amount of sugar in Coke. So we'll be using measurements of mass and volume, and we'll be combining masses and volumes to produce a new property, an intensive property. Intensive means doesn't depend on how much stuff there is, but it's an inherent property of the substance called density. And density is the mass per unit volume. The unit on density is grams per milliliter, the unit that we'll be using, although there are a variety of different units that could be used. And so density is an interesting property because it can be transferred from one type of measurement system to another. So presumably if you measure the density of Coke and I measure the density of Coke, even though we didn't do it on the same amount of Coke in the same place at the same time, we should end up with the same answer. So intensive properties turn out to be fairly useful. So you will be measuring mass using a balance, and you'll be measuring volume using a volumetric flask, and I'll have a little bit more to say about that as we go along when I get to the procedure section. The basis of this whole experiment is essentially that sugar weighs more than water. And when we say weighs more, that's a little bit misleading. What we're basically saying is that sugar has a higher density than water. Water has a density of exactly, well, pretty close to 1 gram per milliliter. Sugar has a little bit higher density, and so when you actually mix the sugar in with the water, you will end up with a slightly different result for the density of the substance of the solution, excuse me, which is a combination of the water and the sugar. So for instance, if you measured the density of Coke and you measured the density of Diet Coke, you would find that they actually have different densities because the sugar in Coke weighs more than the non-sugar substances in Diet Coke. So interesting application. But not one that we're going to pursue here. We're only going to take a look at Coke itself. So Coke, we mean Coca-Cola, of course, registered trademark of the Coca-Cola Corporation. So one of the key concepts of this experiment will be something called a calibration. And again, as I'm switching these slides, if you're not catching what I'm saying, remember that you've got the time bar at the bottom that you can use to go back to a particular slide and rehear the information that was presented on that slide. And the time bar has those vertical marks that show where I transition from one slide to the other. So again, one of the key concepts here will be the idea of calibration or standardization. So in a calibration procedure, we're basically going to be making measurements and we're going to be comparing to known substances, and those known substances are referred to as standards. So this isn't really that crazy of an idea. If you think back to the original old balances. So this is what a balance used to look like. This is the type of analytical balance that we use in the laboratory these days, but this is what the old balances used to look like. And there was a balance, you know, basically two bands that would balance when you put the unknown substance here and put weights with known masses here, and when you put exactly the same number of masses over here as you had unknown mass over here, you would get the thing to balance, and that was a sort of a primitive version of a calibration, or standardization. So we're using known masses over here and comparing them with unknown mass over here. Interestingly enough, the same thing happens for these really fancy electronic balances that we use in the laboratory these days. So these fancy electronic balances produce a number, an electrical signal, that's proportional to the amount of mass that's deposited on the pan up here. And so someone had to go through the trouble of measuring those electronic signals for known masses that had been deposited on the pan, and deriving the relationship between the electrical signal and the mass of substance that was placed on the pan. And that person was clever enough to program this display here to read out mass in grams rather than electrical signal, which would be proportional to mass in grams. So some very clever engineers were involved in the process of determining that relationship and actually programming this device to read out directly the number that we would like to have. But I should point out that this calibration procedure, which uses known masses, has to be performed every once in a while. So every couple of years we pack up all of our balances and send them off to the factory, or have somebody come in and actually put known weights on them and recalibrate them and adjust them if necessary. So this electronic display has a built-in feature that allows you to change that calibration if necessary, if it changes over time. And one of the ways that it changes over time, I should point out, is that things get dirty. So be very, very careful when you're weighing stuff on the analytical balances and the balances that are in the labs to keep everything clean. Be very conscious of not getting little minuscule amounts of solids down inside of these balances, and they'll behave, and they'll be very, very useful devices for you in the future. They're extremely accurate and precise, very good measurements to use. Okay, so in this case, we're going to be measuring something, and we're going to be establishing the relationship between the measurement and the property that we desire. So the measurement in this experiment is going to be the density of the solutions, and the standards that we're going to use are sugar-water solutions. So we're going to dissolve sugar in water, and we're going to use Coke as a sugar-water solution. And we're going to measure the density, the mass per unit volume of all of the different standards and the unknown in this case, which is Coca-Cola. So the measurement is density, and the known relationship is the amount of sugar, the mass of sugar that we place in a known volume of water. So interestingly enough, the two things, the measurement and the known property, will be the same unit, grams per milliliter, mass per unit volume. But in one case, we'll determine the density based on a measurement of volume and mass, and in the other case, we'll know what the relationship is based on the amount of sugar, the volume or the mass of sugar that we place in a known volume of solution. So again, you know, the same unit on both of them. One of them is a measurement, one is a known, and then we will establish the relationship between the measurement and the property desired, and finally we'll use a comparison to determine the property of the unknown. In this case, the mass of sugar in the known volume of Coke, and then by extrapolation in the can of Coke. So this middle part, establish the relationship between the measurement and property desired. So we're talking about a mathematical relationship, an equation that describes the relationship between the property that you're measuring and the known property that you've established for the range of standards. So as an example, I've shown some data here, and the data is plotted in a graphical form, and we will expect you guys to be able to plot graphs to construct graphs. So to use Microsoft Excel, that's available on the computers in the lab to construct these graphs. The figure you've probably already done it by hand in some of your classes back in high school, but what you're going to be doing is constructing graphs like this. And when you say that a graph is constructed that plots a property versus another property, you have to be clear about which thing you mean in which case. So we typically refer to this axis as the y-axis, and we typically refer to this axis as the x-axis. When you talk about a graph and you say something is plotted versus something else, the something, the y-axis, is the thing that comes before the versus, and the x-axis is the thing that comes after the versus. And so in this case, we would say this is a plot of density of solution in grams per milliliter versus the mass of sugar dissolved in the solution per milliliter solution in grams per milliliter. So This coordinate here, the y-axis, is referred to as the dependent variable, and this axis here, the x-axis, is referred to as independent variable. So what we've done is we've constructed axes. We've labeled the axes. Keep in mind you have to do that for every graph you make in this class. And then we've placed the points on the graph. And so the points are basically an x and y pair. So the x in this case was the known value. The mass of sugar was 1 gram per milliliter solution, and the measured density is 2 grams per milliliter, or something like that. We're just using example data in this case. So we're plotting the individual points, and when we get through plotting the individual points, which you will do as a scatter plot within Excel, be careful you select scatter plot because that's not the default in Excel, and we will just plot points, so individual markers. You will establish the linear relationship between the points and the between the dependent variable and the independent variable, between the measurement and the known values. And this linear relationship is something we typically like to see in chemistry because it makes the math really simple. So the equation that describes what happens when you have a line is y equals mx plus b, and I'll type that in over here because I forgot to put it on the slide. So y equals mx plus b, and the idea behind that relationship is y is the again, the dependent variable, x is the independent variable, m is one of the parameters of the fit, and b is one of the parameters of the equation. So b represents the y-intercept, where the line crashes into the y-axis, in other words, where x becomes equal to 0, and m is the slope, so that's the rise over run. That's the increase in the measured property, the y property, over the increase in the x property. The slope is the slope of the line is that property. And those are the two things we're trying to determine in this experiment. It's the m and the b that goes with our chosen y and x. So the way that you do that in Excel is there's something built in after you create a graph called a trend line, and there are instructions in the lab manual about how to run one of these, to create one of these trend lines. And when you create the trend line, the line will actually show up on the graph, as it should, because that shows the relationship of the data. And it also will show up as an equation on the graph. And this is a rather boring equation, y equals 2 times x, because I use some made-up data. This is not what your data will look like. And so something is missing from this equation. So y equals mx plus b, y equals 2x. The thing that's missing is b, because b in this case is equal to 0. The y-intercept is equal to 0. And you may end up with that case. You may end up with a set of points that extrapolates back towards 0, and so b may be 0 in your case, but it probably will not be. M in any case should be a number, and it probably won't be 2. So you probably will get some value of m and some value of b when you ask for this equation to show up on the chart. This equation clearly is pretty small. It says y equals 2x, but it may be difficult to see on your monitor. Typically, you'd want to make that big enough that the TA who's grading a report can actually see it. So again, you construct the graph. You put the points on the graph. You use the linear regression program, which is called adding a trend line, adding a linear trend line. So the words that are sort of used interchangeably are the best fit line, the linear regression, or adding a linear trend line. Those sort of all mean the same thing. And the procedure within Excel will create this line that goes through the points, and it will also create this equation for you that you can use to find out what the unknown is. So now let's talk about how you get the unknown. So all of these solutions that are plotted on this graph were known solutions that we made up ourselves. So we knew how much mass we put into a given volume of solution, how much mass of sugar we put into a given volume, and we determined what the density is, and we plotted this graph. The next thing we do is do the same experiment with sugar, or with Coke. So we don't have to put the sugar in, but we do have to put it in the volumetric flask to find out what the volume is, and then we need to weigh it on a balance, and that'll tell us what the mass is. At that point, we have the mass and the volume. We can calculate the density, and so the density of sugar, Coke, let's say, just for argument's sake, is 7. So we find 7 on the y-axis because that was the measurement, and we draw a line from the y-axis over to the, so we draw a line from the y-axis over to the calibration curve, and that's our value that we determined in the laboratory. And then we extrapolate down from the calibration curve to the x-axis, and that value, y equals 7, x equals about 3.7 or something like that, becomes the answer in this case. So what we've done is we've used a measured property and a known relationship to extract the piece of information that we desired, which in this case was the mass of sugar per milliliter of solution of Coke. And then we can scale up from mass per milliliter to mass per can of Coke, which is a pretty straightforward thing to do. And the density of, or the mass of sugar in a can of Coke is actually given on the label, so you should be able to compare the results that you get to the results that are given on the nutritional information on the can. And I should be making air quotes when I say nutritional information, because there's not much about Coke that's particularly nutritious. So we're going to use this whole process of the calibration to make this measurement, and it's very important that you understand all the pieces of it. So you make the standards in the laboratory, you do the measurements on the standards, you create this graph, you put the line on the graph, you use the line to establish the relationship between the unknown's measured value and the unknown and desired value. I should point out that this procedure that I've shown with the lines connecting a y value to the, and I keep pointing at it, but I'm not saying it, or should be doing it this way. So extracting a y value to the curve itself and going down to the x-axis. That whole thing can be done mathematically by using this equation and basically plugging in the known y value, the measurement of the density of the Coke, and solving for x. So you should be able to algebraically rearrange the expression for x equals something in terms of y, m, and b. If you're having trouble with that, ask your TA for help. But you should be able to get a mathematical version of the answer as well as this graphical version of the answer, and those two answers should be almost identical, so they should give you the same answer. And that's a nice way to confirm that you did everything right. Okay, so you've kind of gotten the idea of the calibration procedure. You'll see it in action. Hopefully you'll get good data that follows a linear trend, and that'll make it really easy to actually determine the unknown property. There are a couple of safety notes and a couple of procedural notes that I want to go over to make your life a little bit easier when you're in the lab, and then I'll say something about the report. Safety, don't drink the Coke. It sounds a little silly, but it makes sense when you think about the fact that we were dealing with potentially poisonous substances last week, and we were holding them in the same glassware that we're putting the Coke in this week. So if you didn't want to put lead nitrate in your mouth last week, you probably don't want to put the Coke in your mouth this week, because it probably will contain some amount of the lead nitrate that you were working with last week. So never eat anything you make in the chemistry lab. We will be very careful about that. There's always possibility of contamination, and there's no reason to run the risk of accidentally ingesting poisonous substances. And by the same token, don't eat the sugar. So that's pretty straightforward. There really aren't a whole lot of safety concerns in this case, but you will be wearing your goggles regardless, as we always do in the laboratory. So procedures. We're going to be working with balances, and one of the things that you'll learn about balances is that you can tare them. And tearing means to put something on the balance that has a mass, but you don't want to include that mass in the measurement. And so one very typical example is we use weighing boats to get an appropriate amount of a substance, a solid substance generally. And so you put the weighing boat on the balance and push the button that says tare, and it'll make the balance go to 0. And then when you put sugar into the weighing boat, the mass will go up from 0 rather than going up from what the original mass of the weighing boat was. So that's a neat strategy for getting the known masses of the sugar that you'll use in this case. But you shouldn't use that when you're actually doing the measurement. What you should do in this measurement, because it's going to be a difference measurement between the volumetric flask with the sugar and the volumetric flask with the solution, is you should always 0 the balance, which is to say you should push the tare while nothing is on the balance, so that 0 is 0. And then when you put the volumetric flask on the balance, you will actually get a weight that goes up from 0. So you probably will use both procedures in this lab, and the TA will show you how to do both. But tearing is useful when you're getting a known quantity of sugar, or an approximate quantity of sugar. In this case, you don't have to measure very carefully what the sugar is in the weighing boat, because you're going to do this very careful version of weighing it using the zeroed balance and the differences between the mass of the flask with and without the sugar. I should point out that the volumetric flask that's used in these experiments will be similar to this one shown over here, and it'll have a big ball down at the bottom that contains a lot of volume, and it'll have a thin neck with a mark inscribed on it, and you will be filling to the line on the neck. Now, one thing you should be really careful about, two things you should be really careful about. The first thing is the instructions state that you should put the sugar and the water only up to about halfway in the flask, and then you should get the sugar to dissolve, and that's very important because if this flask is completely filled and there's sugar sitting in the bottom, it's really hard to get it to go into solution. It takes a lot of inverting in the flask. So you don't want that case. You want to put about half full with water and the sugar that's in it and get it to dissolve, get the sugar to dissolve in the water before you start filling up into this part where it's very difficult to get a lot of movement of liquid. And then the other thing is when you start filling this neck part, it fills much more rapidly than it does down here. And so when you get up in this part or you get very close to the line, you get within a couple of inches of the line, you should do that last bit of filling with an eyedropper so that you're very careful about sneaking up on the line, because if you blow past the line, there's no way to take the volume out and get an accurate measurement, so you have to dump the whole solution and start all over again, which is really time-consuming and painful. So as you get closer and closer to the line, go slower and slower and be more and more careful about adding this stuff. And basically what you're trying to do is hit the line exactly. And those of you who are familiar with this procedure will recognize that there's a meniscus. There's sort of a curved surface on the liquid, and you want to hit the line exactly with the bottom of the meniscus, the bottom of the curved surface. And again, your TA will show you some of this stuff if you haven't ever seen it before. The volumetric flask, when used right, is extremely accurate and precise. We will be actually starting with the volumetric flask by itself with its stopper and weighing that. We will put the sugar in it, and then we will weigh that combination, and the difference between the weight with the sugar, the mass with the sugar in it, and the mass with the sugar out of it is the sugar's mass. And then you will fill it with liquid, and you will do the same trick. And so the mass of the solution will be equal to the mass of the solution plus flask plus stopper minus the mass of the flask plus stopper. Now, we don't really expect the mass of the flask plus stopper to change. And so if you are using the same flask over and over for all of the 5 standard solutions and for the Coke, we don't really expect that mass to change. And if that mass doesn't change, that means you don't have to dry the flask in between each operation. So each time you dump out the solution, rinse out the flask really well to get ready for the next solution. If you're using the same flask over and over again, you can assume that the dry weight stays the same, and that means you don't have to get the flask absolutely empty of water and solution in between the experiments. And believe it or not, that might actually be faster than trying to get the flask completely dry, because people spend a lot of time with paper towels and air and trying to get the flask dry, and it just doesn't seem like it's really all that necessary. Okay, so hopefully you'll see that and kind of understand it when you get into the lab. So be careful about using the volumetric flasks, and you will get very nice, accurate results. Be sure that you're clean and careful when you're working with the scale, with the balances, because the balances can be very precise and accurate instruments if we take good care of them. So the last bit is about writing the report. So some suggestions on writing the report. You will have to make a table of data, and you will have to make a graph. And both of these things will be made in a word processing language, most likely Microsoft Word. So as stated in the last report that I talked about, you will have to actually create a table, and you will create a table caption, and you will create column headings and row headings. We give you an example of a possible data table in the lab manual, and so that's a good place to start. Kind of gives you a feeling for what tables, headings and stuff look like. The graph, we've also got some examples of graphs there, so you can kind of look at those examples, and you should be able to create a graph within Excel and pull it directly into the Word document. Make it fairly large so that it's easily readable for the TA. The directions say something like a half a page. That's a pretty good watchword. And you can typically embed that graph within the text, so you can put text around it, including the caption. So there should be captions on both the table and the graph, and the caption on the table goes above the table and says something like Table 1, a very brief description of the data that's in the table, and the caption for the graph goes below, and it typically says something like Figure 1, and then the description basically is what is in the graph and perhaps even a little bit of interpretation of what's in the graph, although you don't have to go very far with that. The next thing you should do, though, after you construct the graph and put the caption below it, is describe the graph. And my suggestion is to put a little bit of text above the graph that says what it is. So it's the presentation of the determined densities of a range of sugar solutions plotted versus the mass of added sugar in each of the solutions. Or something to that effect. And then below the graph, you want to tell the person that's reading this document what they should think about the graph, what they should take away from the graph. What does the graph show? And so things like it shows that there's a linear relationship between density and amount of sugar added. That's a pretty important conclusion, and that is really what allows you to do the linear regression and actually get the unknown amount of sugar in Coke. So you should make comments about what the graph shows you. You know, obviously linear is a good thing here. If there's scatter in the data, or if some of the data looks a little odd, you should comment on that data. You should say, oh, as we got to higher and higher amounts of added sugar, things appeared to change a little bit, or the point at 5 grams of added sugar looks a little bit different than the rest of the points. So something about the data and what the person should see when they look at the data. And basically what you're telling them is, this is what I see in the data, this is what you should see in the data. So all of those are really good principles to kind of get in the habit of doing, and they will serve you well throughout your college career and writing reports and beyond, hopefully. And so the last thing that you might do is, and I'm not sure that you want to write about it, but you do a little fun mental exercise, which is basically think about the volume of sugar that's in a can of Coke. So you've determined the mass of sugar, and you have a pretty good sense for what the density of sugar is from having weighed the sugar itself. And if you think about that, you can kind of get an idea of how much sugar is in a can of Coke volumetrically, and it's a pretty startling amount of sugar that must be sitting there in that can of Coke. Again, kind of gives you some context on why people think it's not a good idea to eat a whole bunch of sugar. Okay, so that's all I wanted to do here, and you know, have fun with this experiment. It's one of those real life connections, but the whole idea of calibration is very, very important in chemistry, and so that's the chief thing that we're trying to get across to you in this experiment, is this idea of making measurements and constructing a calibration that represents the relationship between the measurements and the desired property. So hopefully you'll get a lot out of this experiment and have some fun with it. Thanks very much. Bye.